Welcome to Improving Disaster Response with Machine Learning. My name is Antje Barth. I'm a big machine learning enthusiast, and I also happen to work as a principal developer advocate for AI and machine learning here at AWS. I'm joined today by my colleague, Chris Freckley, who is a principal specialist SA for AI/ML. In this session, we will show you how a community of developers came together through the AWS Disaster Response Hackathon to build models to support natural disaster preparedness and response. But before we start, I want to show you a quick look at some of Amazon's disaster response and relief activities. All right. Now, I want to start by giving you a little bit more details and a little bit of introduction around the AWS-specific disaster response activities. In particular, I want to show you and introduce you to the AWS Disaster Preparedness and Response Program, which we partnered with for our hackathon. We'll then dive deeper into how machine learning can help improve disaster response with a focus on the hackathon and the top 5 winning projects. I will also share some additional resources for you to learn how to get started with data science and AI/ML on AWS, and if you're curious to learn more about the AWS disaster response efforts. So let's get started. As we can all witness around the world, natural disasters such as hurricanes, typhoons, floods, and wildfires are increasing in both their frequency and their severity. This places an increasing pressure on organizations, including nonprofits, governments, and international organizations, to do more with the limited resources that are available. However, many of those organizations face technology and/or financial barriers to deploying cutting-edge solutions in disaster contexts. At AWS, we believe that technology has the power to solve some of the most pressing challenges in the world. Our disaster response and preparedness team, a key pillar of our commitment to social impact, works around the clock to help organizations leverage cloud technology as they prepare for and respond to natural disasters, contributing our technology, expertise, and resources in the process. For example, with contact center solutions that enable response agencies to rapidly deploy and scale to handle unexpected spikes in call volumes, or edge solutions that enable drone imagery processing at scale in disconnected environments. Let me show you some examples. Following the eruption of Hawaii's Kilauea volcano in 2018, a US Geological Survey showed the USGS facility hosting some of the agency's critical data sets was at risk of being impacted by the volcanic lava flow. They had 40 years of on-prem data that needed to be transferred into the cloud. The USGS determined that the risk to the facility was too high, and they reached out to AWS disaster response program for assistance in quickly migrating their critical data sets to the cloud. And AWS immediately responded by expediting an AWS Snowball Edge device overnight to the USGS facility. And you can see it here on the pictures. USGS staff was then able to quickly download the critical data sets from their on-premise service to the AWS Snowball Edge device. And once the data transfer completed, USGS was able to easily and securely ship their data on the AWS Snowball Edge to an AWS region of their choice. AWS then uploaded the data from the device into the USGS environment running on AWS. Here is another example. When Hurricane Dorian struck in the Bahamas in 2019, it set the record for the worst natural disaster to strike the Bahamas and became one of the 2 most powerful storms ever to make landfall from the Atlantic Ocean. AWS Disaster Response Team volunteers deployed to support the response in a few ways. The team deployed with NetHope to help set up connectivity and communication networks for medical facilities and shelters in Nassau and Abaco. They also supported Help.NGO, an international non-governmental organization specializing in risk reduction and response. Help NGO's Disaster Immediate Response Team works to fill the void between a time when the disaster occurs and the time when a traditional response effort ramps up. Help.NGO was engaged to fly drones to collect imagery to assist with humanitarian response activities in the most affected high-risk areas, including Abaco, Marsh Harbor, Elbow Key, Man of War, and other key areas. AWS Disaster Response volunteers deployed in support of Help.NGO. We provided AWS Snowball Edge devices, as you can see here again on the pictures, to help process that aerial imagery of the damaged areas, which increased the efficiency in assessing the impact. Besides contact center and edge solutions, we also have AI and machine learning solutions that become increasingly relevant. They can help organizations automate risk assessment before a disaster strikes and expedite damage assessments in the immediate aftermath of a disaster. To help stimulate new ways to apply machine learning to solve some of the most pressing challenges in disaster response, we launched the AWS Disaster Response Hackathon this past December. Let's have a quick look. The hackathon started during AWS reInvent this past December with the launch of Amazon SageMaker Studio Lab, a free machine learning development environment. We asked the community to come together and think about creative ways to apply machine learning to solve some of the most pressing challenges in natural disaster preparedness and response, and use SageMaker Studio Lab to prototype machine learning models and solutions. And the response was really impressive. We wrapped the hackathon in early February this year with over 1,400 participants joining the hackathon from over 80 countries worldwide, and we received 42 final project submissions. Let's now move on and have a look at some of those projects, in particular our top 5 winning projects. Before we start, we want to give you a quick overview of the tools that have been used, some of the AI/ML frameworks and data sets that can help building AI/ML solutions in this domain of disaster response. One of the tools we asked the participants to leverage is SageMaker Studio Lab. Studio Lab provides free compute, including CPU and GPU, up to 15 GB of storage and security, all at no cost. That is right. There is no cost involved. You don't need an AWS account. You don't need to worry about setting up infrastructure, managing it. You can simply provide a valid email address to sign up and request an account. Studio Lab also comes with GitHub integration, so you can share and persist your work throughout the project. So it is really the perfect starting place for ML coders. And now I'm handing over to Chris, who will give you a sneak peek into the code of the winning projects, and will also give you an overview and summarize the data sets that we've seen the teams used, and give you also a quick run through some of the exciting ML frameworks and models. And with that, Chris, over to you.
Hey, thanks, Ancha. Hi, everyone. My name is Chris Fregley, and I am a Principal Solution Architect for AI and Machine Learning at AWS. And today, in this part of the talk, I'm going to walk through some of the code. On the left, we have the winners and some of the submissions for this hackathon. And I'll step through some of the code repos, and then I'll show a quick overview of the Amazon SageMaker Studio Lab that was used to submit these projects. And I've actually sort of analyzed the top winning solutions and extracted out some of the patterns that I saw and some of the data sets that were being used and some of the file formats. And so I'll quickly start with a brief overview of the top winners, and then I'll step into how to actually use SageMaker Studio, and we'll talk about GPUs and some pretty interesting stuff here. So let's start by making this window a bit bigger. This was the Response Hackathon, Disaster Response Hackathon, used by SageMaker Studio Lab. So let's get to, this was the third place submission, and this is a really, really cool project where the team is using computer vision to analyze any hazard fuels that could lead to these wildfires. And so looking at diseased trees, the estimated mortality, and so really cool stuff. So let's jump over to the GitHub repo. And you'll see in these repos, there's this Open Studio Lab. Open this project with Studio Lab. If you click that, that'll actually open it. I'm going to hold off on that for a sec because I just want to show a quick overview here. We do have a section that is going to go into more detail from the actual teams themselves. And so, I'll let you watch those here in a bit. But just know that we're, dealing with ImageNet data sets. We're looking at data sets from the Forest Service. There's something called the Insect and Disease Detection Survey, IDS. And these are all open data sources that are on the AWS Open Data Registry. And so I'll show you how to get to that here in a bit as well. Okay. So that's the GitHub project and goes into much more detail here. If you step into some of this code, you could reproduce this code again by going into the free Studio Lab environments. Second place winner, the thunderstorm prediction. This was really cool. This is actually finding correlations between atmospheric conditions and then trying to predict when there's going to be lightning strikes and where these could occur, and also thunderstorms as well. And so that's the submission. Here's the actual code behind it here. And again, you see the open in Studio Lab. Talking about sort of the problem inspiration here about lightning, how this, can potentially kill 24,000 lives per year, 240,000 people injured because of thunder and lightning, specifically lightning. So pretty cool stuff here. This is really the high-level summary. We will dive more into this in a bit, but this is the GitHub repo. If you want to reproduce this, click into Open Studio Lab here. First place winner, this is a project called Déjà Vu. deja vu maybe, is a disaster response solution. So this actually helps with the response portion of these disasters. Okay, and so the first two were more sort of mitigation prediction, and this one really dealt with how do we respond once these things happen. Okay, so that's the submission. Here's the actual code here, and I believe this project actually also comes with a slick demo that you can run, and has a nice UI. Actually, I think 2 or 3 of these submissions actually have a nice UI. That's kind of fun to go through. But again, we'll show more about these projects in a different segment of this talk. Okay, so if you want to reproduce any of these, you can certainly go and click Open Studio Lab here. But the idea is to really see, where is there damage, and potentially, help people figure out how to get out of here, where to flee, which roads are not damaged. So, pretty cool stuff here. Okay. There was a best technical implementation and functionality. So there was an honorary award here, and this goes to Global Fire Spread Prediction System. So this is a team at a place called Satellite View that is using their knowledge of wildfire, satellite imagery, machine learning to help detect, fire spread, and how can this be applied globally as well. And so this was a really, really cool implementation, a lot of good analysis in here. Let's show you the repo. Now, one thing I'll get to in a bit when we switch over to Studio Lab is there's actually quite a lot of just pretty basic, classical machine learning that we saw being used with a lot of these projects. So, of course, there's going to be computer vision, and of course, there's going to be, pretty advanced data sets, satellite imagery. But at, really the end of the day, there's a lot of just logistic regression and classification and binary classification. And so, pretty, if you're familiar with sort of basic machine learning concepts, these projects are, very, very understandable. Okay, and so this is really trying to predict, based on satellite imagery, and some of this satellite imagery actually can come, within 3 hours or in near real time, and so we'll talk about some of that when we get to the data sets. Let's jump over here to the best solution to the challenge. So this is a group called Soteria. And again, they're using machine learning with satellite imagery to map the sort of current state of these disasters, these natural disasters, to help people respond, to get the emergency vehicles and people on the ground to these different locations. So really, really cool project. A really great use of machine learning, and we'll dive deeper into that solution. Here's the GitHub repo. And let's jump over. Okay, so assuming, and I've kind of done this behind the scenes just to speed things up a little bit, but if I bounce over to here and make this screen a little bigger, I've got, let's see, 7 notebooks here, and I'll try to get to as many as possible given time. There were some very interesting findings. For example, clouds. Clouds from these satellite images can really cause problems, and they're often interpreted as buildings. Okay, so let's see, file formats and data sets. There's this GeoJSON file format that is pretty cool. So it's a specification that gives you support for these multi-polygons. You can also then give all kinds of different custom properties. And so, this is different regions, different, let's see, there's, free-form notes, there's observation counts, the way that this data was collected, and basically a whole ton of parameters that you can load in. And what we'll do later, I'll show GeoPandas, where you can actually access this data and manipulate it just like a regular pandas data frame called a GeoPandas data frame, GeoData frame. Okay, and then here's the typical multi-polygon. So we have the coordinates, and this really defines those like edges for that polygon. There's also something called GeoTIFF format, and really this embeds spatial information. So these are just like regular TIFFs, but they actually have spatial coordinates and the cell size of these raster images, and they will also include the coordinate reference system, which is very important because when you're trying to compare and do operations on these GeoTIFF images, you really need to know what is the reference coordinate or the like coordinate reference system, because you have to match those coordinate reference systems when you're joining different like images or trying to create larger dimensional spaces out of lower dimensional TIFFs. There's one other format, pretty cool, called Cloud Optimized GeoTIFF. I believe Amazon was actually part of this many years ago. And this is a way to, if you have very large files, you can actually stream them when you're doing your like analysis or doing machine learning, so that you don't actually have to download the whole file up front, but you can stream it. And the technical details here are that these cloud optimized GeoTIFFs do support HTTP GET range requests, and really helps speed up some of the analysis. One link I'm going to open up here, and I do have links in here. I'll also share a link where all of this is, this code, but there is the AWS Open Data Registry. Now this is pretty cool, and we've actually provided a tag here with disaster response, and here's your Landsat data sets. So these are open data sets that you can use. These are stored in S3 buckets. Okay, some of the cool libraries we saw, GeoPandas. This is a pretty cool, so it implements GeoSeries and GeoDataFrame, which are subclasses of the classic Pandas series and Pandas data frame. This really lets us work with geodata just like we would work with regular tabular data. So very, very cool project. There's a library called EarthPy, and it's devoted to working specifically with these sort of spatial images, GeoTIFFs, and like vector data, and yeah, so really lets us. And yes, actually EarthPy and then Raster.io are used together to load in these GeoTIFFs, right? Which are, they are not just regular images, but they have the image, but they also have a lot of this other spatial, coordinates that are embedded within. And Raster.io gives us a Python API that really lets us deal with these GeoTIFFs using, sort of NumPy, like n-dimensional arrays. I mentioned there was a lot of classical machine learning, a whole ton. scikit-learn was used everywhere. It's not specific to this domain, but it certainly does come up in pretty much every machine learning project that I am part of. And so some of the popular models that we saw being used were k-nearest neighbor, principal component analysis, SVD, tsne, binary classification, multi-class classification, logistic regression, decision trees, and random forest. Very, very popular. Got very, very good results with these simple like algorithms. This specific notebook I'm showing here is more generic and not specific to any of the winners, but it's showing the fundamentals of how each of those winners has gone about this. Of course, using GPUs, using GeoPandas, things like that. So this is a weather image classification. So these are images of different weather conditions, and we want to classify them into one of four categories: cloudy, rain, shine, or sunrise. Okay, not quite sure how they got these four or why these were significant, but that's the data set that we chose here. And one thing to point out, if you use a GPU, this takes 25 seconds. This is using PyTorch and something called Torch Vision. So computer vision with PyTorch. If you use a GPU, it takes 25 seconds. When I was first doing this and I was only using a CPU, I was not using GPU, this actually took 8 minutes. And so this is almost 20 times speed up to use these GPUs. And yes, the GPU does cost more, although it's free within SageMaker Studio Lab. When you can do this 20 times faster, you can get the answer quicker, you can iterate faster, and the summary here is always use GPU if you can. Here's a traditional pandas data frame. The point here is to show GeoPandas data frame. We can convert that regular pandas data frame into a GeoPandas data frame by just wrapping it here and then giving some extra information about the geometry. And now there's another column here added, and so this is pretty cool. When you plot a GeoPandas data frame, it'll actually show you, which continents. South America, here we've plotted different cities and countries within South America, and it actually shows up on a plot like this, okay? So pretty cool stuff. Saw this being used very heavily, throughout all these projects. Something is, or that is very unique to this type of geo analysis. Next one, EarthPy. And so like I said, EarthPy and Raster.io, these are used to load in GeoTIFFs. So you'll see the TIFF extension. This is actually a GeoTIFF, which has the extra data in it for the spatial coordinates. Okay, and here is so DEM, again, is a digital elevation model. There's also this concept called a hillshade, which is a 3D representation to sort of, add a little bit more three-dimensional and visually interesting aspects. So this is without the hillshade. Now this is using EarthPy, by the way. That's what EP is. And now we're going to add the hillshade. So this is the actual elevation with some nice shading here. We see, cities over here. We see some of this type of elevation for these hills. And now we can actually combine the two, where we combine the elevation model, the color model, with the grayscale hillshade, and now we see a very, very interesting and fun way to analyze this data. Okay, and let's see. We go to the next one, California lakes. So, living in California, I enjoy learning more and more about the state that I live in but did not grow up in. So I like this data set quite a bit. What we're going to do here is we're once again going to use GeoPandas. We're going to plot and find some of these specific lakes and within certain counties. So pardon the scroll, but I'm going to get to the visually interesting stuff here. So here we're just plotting the counties within California, okay? And I live in San Francisco County, so way up there. And let's see, let me keep going here. Once again, apologize for the scroll trying to get through. Okay, here's the lakes. So we have two separate, so up above I had shown counties. Here I'm showing the lakes. Okay, and this is using GeoPandas, and this is plotting. Is this using? Yeah. Okay, and then I had mentioned before that we have to be careful with the CRS, coordinate reference system, because when we try to combine these different images and these different shapes, the coordinate reference system has to match. If it doesn't match, things won't look good. And so we see one of them has slightly different CRS. So the counties and the lakes data have a different CRS. So we need to project. In this case, we're choosing to project the lake data into the county data. And now they're both in the same CRS projection. We can overlay and then visualize. So this is a combined way to look at the counties and the lakes. And so again, I'm showing these as fundamental building blocks that we saw in a lot of our submissions, doing things like this with road data. Okay, And here we're specifically here looking at Lake Shasta, pretty cool lake that I don't know too much about, but I learned more from this notebook, and here we can actually plot what it looks like. So pretty cool. These are typical plots that we usually do with pandas and matplotlib. All right, one last data set. This is really more about atmospheric. So this is NOAA, the National Oceanic and Atmospheric Administration. And this actually comes from, on the East Coast, a town called Asheville, North Carolina. Very, very cool town. I've heard it's very similar to Boulder, Colorado, San Francisco, kind of a sort of hippie-ish town, which I'm always into. I like that kind of stuff. Here's the actual data set. So we see soil temperature, soil moisture, surface temperature, a lot of cool things. Here's the units that are being used. Everything is Celsius. And what are we using here? We're using pretty standard things here. So matplotlib. So a lot of, okay, here's the data prep. I'm just going to get through this quick. This is really a pretty standard, tabular data type of notebook. It's just analyzing tabular data. So looking at, mins, averages, describing these data frames, telling us what the types are. And so not so much geo-specific visualizations here, but, more your typical tabular data. But let me get to the interesting stuff here. So here we can very quickly look at these histograms. So we see, what is the makeup of our data for each of those data points, where, on the y-axis here, of course, is the count of the number of times that we see, longitude at negative 82.5. Again, this is a single town within the US just to keep the data manageable. So we see the same longitude, the same latitude for all, 1,000 plus rows. And then we can see the maximum temperature, surface temperature, and let's see, soil temperature, humidity. Here we're just trying to look at how many rainy days are there. Just 1 second, let me get to that. Right, so here we have added a new column based on a new fields that we're calling rain labels. So up above, I kind of skipped through it, but we created a new column that has really, thresholds. If there was no rain, if there was 1 day of rain, 10 days of rain, 20, represent different. So this looks like a pretty rain-free town, and maybe a town I need to, potentially move to because I don't really like rain. I like sunshine. And we can look at some, fun box plots here. Let's keep going though. This is a fun grid. This is really comparing solar energy, the radiance with the average air temperature. We see there is not much correlation actually. So we do notice little correlation between these variables, but let's take a look at the overall coordination between the other variables here. So probably thought there has to be some kind of pair plot in here, and there sure is. So here we see, daily average. Apologize if this is too small, but we can very quickly see what's correlated, what's not correlated, and we can dive deeper into this. Wet is blue, dry is red. Okay, and you can take a look at all of this in the GitHub repo. And here's just number of dry and wet days per month. So here's 1 through 12, January through December, number of dry and wet. Air temperature is seasonal. So this is from January 2017. It's a little chillier. This is Celsius going up to pretty hot, chilly, hot. So this is what we expect. This is a seasonal, 4-season type of city in the US. And let's dive deeper into looking at, average, max, min. There's another one here showing by month. So this is, month 1 through month 12. This shows us that, in the middle months, June, July, the maximum temperature is much higher, average temperature. So again, this is showing within a single year across those 3 years aggregated, we do see expected patterns here. Last one would be kind of a temperature heat map. And we see, of course, in the middle months, we do see warmer. This is the air temperature based on month, and then this is sort of rainy. This is precipitation, right? And then the last one is humidity. So it looks like sort of year-round things are, pretty humid even when it's not raining. And having been near Asheville, I've never actually been there, but in towns nearby, I certainly know that humidity. So just to summarize here, we've got this registry of the open data on AWS where you can find a lot of these data sets. There's many more than the 44 here. We just in this URL, we have it split out for disaster response. There's actually 300 plus data sets that are pretty cool. And here is the actual data, or the GitHub repo. This is my and Ansha's repo for the book that we wrote. So check that out. You can find these samples in here. And I think that's it. Ansha, back to you.
All right, great. Thanks so much, Chris. We asked our hackathon participants to develop or prototype an AI/ML solution that aligns with at least one of the phases of the disaster lifecycle that you can see here on this slide. For example, mitigation, preparedness, response, or recovery. We also asked the teams to focus on challenges that are present in one or more types of natural disasters, such as hurricanes, cyclones, wildfires, floods, or earthquakes. So let's now move on and have the teams present their projects in their own words. I've collected the top 5 projects, the top 5 winners from our hackathon, and mapped them throughout those stages here. And they will cover the prevention and mitigation, preparedness, and we'll see example of response. Let's start with the first phase, the prevention and mitigation. This team here from Accenture Federal Services focused on wildfire mitigation. They developed a computer vision model to identify dead and diseased trees in near real time using open source Landsat data from their work with federal, state, and local land managers. Let's have a look.
Hazard fuels such as disease and dead trees increase the likelihood and severity of wildfires and associated disasters. However, tree assessment methods are time-consuming, laborious, and require manual assessment. To aid federal, state, and local land managers in quickly identifying and responding to tree disease and mortality, we developed a computer vision model to identify disease and dead trees from open-source Landsat data. On an annual basis, the Forest Service conducts a manual survey of insects and disease detection, or IDS. We use this hand-labeled data, specifically the 2020 IDS, in conjunction with Landsat imagery downloaded from USGS to create our training data, which you can see here. Each of the Landsat geotiffs was divided into a train test split. 80% of the image, what's shown on the left-hand side, was used for training, and the other 20% was used for testing. Briefly, we use a transfer learning approach where we use an ImageNet to produce features and then applied a linear classifier. The outputs of our model can be seen here. In one example, the model output on the left and the ground truth on the right. We were then able to apply our model to a large swath of area, multiple different geotiffs, and produce an output. The output from our model was visualized in our risk dashboard, which you can see here. What you're seeing in the middle of your screen here in the blue box is the extent over which we modeled. Once our model was complete, we created hazard maps for sections of the El Dorado and Humboldt National Forest. Coming over here, you can see our wildfire risk hotspots dashboard, a dashboard we built for forest managers. What you can see in the blue box is the area over which we made predictions for, and the red areas that are shaded are areas that have disease or dead trees, are high-risk areas. You can see main KPIs here that would help a forest manager make decisions. You see the risk area, the total areas of hazard fuels, and a prioritized treatment list here. For our prioritized treatment list, we brought in information such as the total number of acres in the risk area and proximity to different types of infrastructure, such as cell phone towers, fire stations, and hospitals. We look forward to working with forest managers to customize this dashboard, bringing in metrics that are important to them and other subject matter expertise that come from their years of experience working with the forest. Both our repo, our data set, and our model and this dashboard are available, and we'd be happy to discuss any further extensions with you or other interested parties.
Impressive work. Thank you. Now let's move on to the next stage, disaster preparedness. And let's have a look at our winning projects there. This team focused on thunderstorm predictions, and really interesting, by finding correlations between the atmospheric condition at the time of the lightning strike to predict the occurrence of lightning and thunderstorms. Let's have a look again.
Our team consists of data scientists Surya, Aksa, and Shubhangi, domain experts Dr. Ram and Tanya, and advisors Colonel Ritesh, Dr. Ashutosh, and Dr. Vijaya. So lightning strikes have been increasing in the recent years due to climate change and other factors. It has become a danger to both humans as well as businesses. So to explain the scientific context behind our solution, when the air temperature and wet bulb temperature are approximately the same, the relative humidity has maximum value and exerts a surface pressure. So when the relative humidity is between 60 to 80%, there is intercloud flash, and when it is between 80 to 100%, there is cloud-to-ground lightning flash. All of this has been substantiated and validated in the research paper, Effects of Relative Humidity on Electrification and Lightning Discharges in Thunderstorms. Taking weather parameters, we have been able to develop a supervised model to predict lightning up to 30 minutes. These are the parameters that we collected, and the model has been tested on San Diego, Florida, and locations in India. The reasons of the thunderstorm might be different due to geographical locations, but the result is the same. This is a demo of the models we have built. We used SVM, KNN, logistic regression, and decision tree. We also took a threshold of 50 lightning strikes per day to depict dangerous storms. So we encoded it as 0 if it was below 50 and 1 if it was above 50. As you can see, the model is generic and will work globally for lightning prevention. So to conclude, out of the 4 models that we tested, SVM produced the best result. The model has produced 50% accurate predictions, and after tuning of the model and feeding it more data, we aim to get our accuracy to the 80-90s. Thank you.
And again, thank you very much. It's been really impressive to see the creativity in the teams across the hackathon, combining really kind of out-of-the-box thinking in research and science to combine here with actionable ideas in disaster response. The next project also is an example of how machine learning can help in the preparedness stage. This project focused on global fire spread predictions. The tech team at Satellite View applied their knowledge of wildfires, satellite imagery, and machine learning to demonstrate a fire spread prediction system. Let's have a look at this project.
For this challenge, the tech team at Satellite View applied our knowledge of wildfires, satellite imagery, and machine learning to produce a fire warning system. Unlike aircraft or drones, which quickly become expensive if multiple fires need attention, satellites offer continuous global coverage. But with time of the essence in disaster prevention, accurate prediction of fire spread could solve the problem of delays between data collection and publication. Using a NASA OpenAPI and AWS Open Data Registry, we retrieved data from the MODIS and VERS sensors, as well as atmospheric data from the ERA5 reanalysis. Here's an example of some VERS fire data in the form of a heat map, where the colour represents the radiative power of a fire. As we were using data from different sources, we first had to standardise it. This meant mapping all data to a common coordinate system and defining sensible areas to generate training data for each fire cluster, like the one shown here. For each area selected, we passed the current day's fire mask, shown here in red, a map of elevation, as shown in grey, and other features to our machine learning models after inspecting the quality of the dataset. We trained and tested traditional machine learning and deep learning models. If comparable results could be achieved, classical logistic regression or random forest classifiers might be beneficial as they tend to need fewer resources and are quicker to run than deep learning models. We used the precision and recall to assess model performance. Precision shows what fraction of the predicted fire mask was correct, and recall shows what fraction of the target fire mask was predicted as fire by the model. Comparing these stats shows our deep learning model had higher recall, which in this fire scenario is probably more important than higher precision. Both approaches gave slightly better results than a baseline assumption of persistent fires, but show that the prediction is highly dependent on the previous day's fire mask, and the model struggles with big changes. For the deep learning approach, our best model was a ResUnet architecture trained from scratch on the dataset we prepared. This model predicted the next day's fire mask with higher precision and recall of fire pixels than the baseline assumption. This slider shows an example input fire mask on the left and the corresponding model prediction for the next day on the right, overlaid on Sentinel-2 imagery. Here we can see some actual next day fire masks on the left alongside our model predictions. By using OpenStreetMap data, we can also calculate distances between the predicted fires and infrastructure, and warn the user when a fire is approaching buildings with a simple message as shown. Our solution could help governments and emergency services to evaluate the risk to life or environmental damage of a fire, allowing them to target valuable resources. To have a wider impact, our model could be trained on data for a wider variety of locations, as we focused on North America here. We also hope satellite views high-resolution thermal imagery, shown here, could provide fire management services with more accurate information and help them pinpoint populations and areas at risk.
Another great submission here from the team. Thanks so much. Now, let's move on to the stage of disaster response. So once the disaster happened, how can we help here? The team around Disavoo built a solution to direct relief resources to where they are needed most during disaster and after disaster happened, using machine learning. So let's have a look at their project presentation.
Hi, I'm Stephen. Rico and I worked to create Disaster View, a disaster response solution to help allocate resources where they're most needed using machine learning powered by SageMaker Studio Lab and open source Creative Commons licensed datasets. SPB, an American non-profit charity, and the Asian Development Bank have alluded to a problem. There needs to be a better way to determine the extent of damage to both houses and infrastructure to help prioritise recovery efforts after a natural disaster. This is the problem that we are trying to solve, and we solve it by using pre- and post-disaster satellite imagery and sophisticated machine learning models to establish the extent of damage. We then display this data on a map to help show where efforts need to go. So this is what Disaster View looks like. We show two different natural disasters: Cyclone Shaheen, which affected Oman, and Hurricane Ida, that affected New Orleans. Disaster View gives disaster coordinators the ability to quickly flick between before and after satellite imagery and overlay these with locations of amenities like schools and fuel stations. We then start to add our own machine learning generated layers of building footprints and damaged buildings, which allows you to really get a picture of which areas have mostly been affected. This then allows coordinators to send aid exactly where it's needed. The machine learning pipeline consists of two individual models. Step 1 is to take the before disaster satellite image and run it through our first model, a UNet that's trying to predict building footprints. Once we've predicted the building footprints, we then cut out the same latitude and longitude points out of the post-disaster image. We then run this cut-out post-disaster image through a ResNet to predict whether it's damaged or not, and then take the footprints, labels, and visualize them on a map. For the sake of the current iteration, we have only focused on hurricanes, cyclones, and tornado natural disasters, and the training data reflects this. We've split each stage of the process, generating the footprints model, generating the building damage model, and the inference pipeline, bringing them together into their own separate notebooks to avoid confusion. Our GitHub repository currently hosts these notebooks and provides links to open directly in SageMaker Studio Lab, and all the data required is currently hosted on an S3 bucket to get you started straight away. The models are trained using SageMaker Studio Lab GPU instance, which presently appears to be using a Tesla T4 GPU. The footprints model seems to be alright. It sometimes predicts clumps of buildings rather than individual buildings, and sometimes predicts roads as buildings. The damage detector model seems to be reasonably accurate, with a recall of over 90% and a precision of over 80%. All of the datasets that we use are either Creative Commons share-alike or Creative Commons non-commercial share-alike. More information about the datasets can be found in our README. Rico primarily worked on the front-end, back-end and integration, and I worked on the machine learning model. Our contact details are available on screen if you have any questions.
Thanks. Another impressive project. Now, we do have another project that focuses on the response stage. The team around Soteria used machine learning with satellite imagery to map natural disaster impacts for faster emergency response. Let's have a look at their take at the challenge.
We'd like to introduce you to Soteria, a project with a mission to address natural disaster response through AI. We're a diverse team of college students passionate about using technology for social good. With a diverse range of natural disasters worldwide happening at any given time, having innovative technological approaches to mitigating these disasters is more important than ever. We wanted to showcase our idea through an applicable context. That's why we've chosen to focus on flooding that happens annually on the eastern coast of Malaysia. But in every weakness is an opportunity, and that's why we've created Soteria, to minimize the risk to impacted citizens and helping the response between first responders and emergency management in the most critical 48 to 72 hours. By using satellite imagery to map natural disaster impacts, we can increase the scope, speed, and efficiency of emergency decision-making.
For the technologies, we use Amazon SageMaker Studio Lab to design and train the machine learning models with TensorFlow. We use AWS to store our dataset and deploy machine learning models. We use Hugging Face Spaces to host our interactive machine learning demo app and Figma to prototype the web app. For our dataset, we use XBD dataset, which has around 4,000 pairs of pre- and post-disaster satellite images with 6 disaster types and 850,000 buildings. So what exactly did we build? We built machine learning models to classify the type of disaster, estimate impacted population, and determine regional damage level with satellite imagery. Here's an overview of the models. The input is satellite imagery. We then pass that to a binary classification model to determine whether a disaster happened or not. We then use a multi-class classification model to determine the type of disaster that happened. It could be volcano, flooding, earthquake, fire, wind, or tsunami. Then we use building detection model to find the buildings in the image. And using this, we can estimate the population impacted in that area. And finally, we have a regional damage classification model that's based on the damage level of each building in the image, and we can output a damage level for this region. So here are some demos for our project. So here on SageMaker Studio Lab, using disaster classification as an example, we first read in the dataset. And organize it. We can see some examples of the dataset. We then build a model, compile the model, and train the model, and then do some analysis on the result. And finally, we save the model, which we then use to deploy to AWS. This is our machine learning model demo app. At the bottom, you can see some examples you can pick. When you submit it, and we can see that the machine learning model predicts there were no disaster happened in the image, the likely disaster that happened were fire, and there were no damage.
This is our web app overall layout. On the left sidebar, it displays location, disaster type, and estimated population impacted. It is able to show danger levels as well as add shelter centers and support and danger zones onto the map while being able to set to regular, satellite, terrain, and live traffic modes. So when you do click the show damage level, the user can see there are 3 different colors of green, orange, and red in the map to indicate the level of impact in each area. Thus, emergency responders could determine where to prioritize. Shelters are also added here onto the map, and key danger areas to be avoided are now labeled. By hovering over help icons, as seen here, responders are able to see requests for specific types of aid. And that is all for our presentation. Thank you for your time.
Thank you. And this completes a quick whirlwind tour through the top 5 projects of the AWS Disaster Response Hackathon. Congratulations again to all the winners It's been amazing to see the creativity and the passion all of the teams that participated put into those weeks during the hackathon. And a big thank you to everyone who participated in this hackathon. We have received so many more exciting and amazing projects. I want to call out 2 honorary mentions that include an AI for disaster assistant to support humanitarian workers and civilians to achieve faster responses in earthquake emergencies. And another team exploring migratory birds, really exciting, in their ability to sense subtle local geomagnetic disturbances in their behavior change resulting to forecast earthquakes. So really some creative ideas. And you can explore all of the projects, if you're curious now, through the project gallery page on the website, the hackathon website, hosted on devpost.com. And if you want to run the project sample code, you can request and sign up for your own Amazon SageMaker Studio Lab account, and then either click on those Open in Studio Lab buttons that you see in the GitHub repos, or simply by using a git clone command to copy the project into your environment. And if you're interested in learning more how to get started with data science and AI machine learning on AWS, I do have a couple of more resources here. If you're looking for a self-paced digital course with hands-on exercises, check out the Practical Data Science Specialization on Coursera that 3 of my colleagues and myself developed in collaboration with Deep Learning AI. It's a 3-course, 10 weeks hands-on specialization designed for data professionals to quickly learn the essentials of machine learning on the AWS cloud. Each of those 10 weeks features video lectures, quizzes, and a comprehensive hands-on lab. If you prefer reading, have a look at the Data Science on AWS O'Reilly book, which I co-authored together with Chris. In the book, we're discussing how to implement end-to-end continuous AI and machine learning pipelines. We have 12 chapters, 500 pages, and over hundreds of code samples also shared in the book's GitHub repo, available for you. And we touch on literally every step in the machine learning workflow, from the data ingest, data preparation, analysis, feature engineering, to model training, tuning, deployment, to building pipelines, and also, of course, securing your data science projects in the cloud. All of the code is publicly available in the GitHub repo that we shared. And we also host global monthly meetups discussing use cases, best practices, and the latest AI/ML technologies. If you're interested in joining us, follow the link shown here. And just as a quick summary here, links if you're interested to learn more about the AWS Disaster Response program, the Hackathon, Studio Lab, and the resources to get you started with data science and machine learning on AWS, including all of the code from this session today. Thank you very much.